Hey there, welcome back. So, yeah, so the thing is that you will be asking uh, why are videos like, why is this video coming out after like 4 or 5 days? So, I forgot to tell you, but videos will be coming on 3 consecutive days on Fridays, Saturdays, and Sundays for um, anyone in the other side of the world. It might be Saturday, Sunday, and Monday. So, uh, yeah. Also, I would like to thank we have 20 subscribers now. This is pretty shocking because yeah, my content is like mostly I'm blabbing about stuff and learning about stuff on camera and yeah. Uh, Thanks to everyone. There's like people that have watched 11.8 hours of my videos, and yeah, 11.8 hours, nearly 12 hours of me blabbing about stuff, and yeah, that's wonderful. So, thank you. I'm grateful to all of you. Okay, let's get back. So, today's video. So, yeah, I'll tell you about that. Okay. So, the course that we are following, we are not necessarily following a course, but I'm making this project. So this is the project for anyone new. This is the project that I'm making. It's called Serial Dynamic Memory Allocation. It's one of the MIT courses, Performance Engineering and Software Systems. You can look it up, and the lectures are present on YouTube as well as on our platform. Uh, and what is one of the lectures, which is lecture 12 or something, uh, we let me just show you MIT Performance Engineering. So yeah, if you look it up, so this is the course, Performance Engineering of Software Systems, MIT Open Courseware. If we go in lecture slides, and this is the one, the 11th lecture, storage allocation PDF. So that is what I have downloaded over here. Let me show you. This is the one. Yeah, I was just reading about it, and yeah, I haven't completed the entire lecture, but I have like you can see half of the video I've covered. So yeah, I'll be completing it. So in this video, we'll be mostly talking about uh, this what I've learned in this lecture. It's like a 1 hour video. So this will be a short video explaining like things in like simpler, and I guess that video is also simple too, but I guess in this video I'm just explaining you stuff. So if you want to take a look at it, please go ahead and watch that lecture. It's like 1 hour long and it is totally worth it. uh, yeah, so let's go. So, yeah, our first problem that you might have wondered, like, okay, let me just show you. uh, I guess you might have watched the previous video. In the previous video we have like covered, so there was an attachment zip file. So this is the attached zip file. This one is the attached zip file, and when we extract it we have this folder. So let me show you what's inside it. Also, I forgot. Okay, first of all, let's cover that thing, because okay, I was going to forget that again. So in the previous lecture, not lecture, in the previous video. Yeah, I'll just add this to the full screen and yeah. So in the previous video, what we did was we took a look at what are all the things present inside this attached document, attached directory. So we have to make changes in allocator.c. Let me just show you what that means. Yeah, so this is like, not this one. Yeah, so this is like the functions that we have to make some changes in. This is like the free, this is my realloc, and yeah, that's it. So we have to make changes in this file, and for that I was thinking like, okay, so our main problem in making this project will be how to manage the freed up memory, because the thing is that if you have the okay, let me just show you that again. I should have opened all of these documents before the lecture, before the video, not a lecture. Why am I saying lecture? Okay. So yeah, we are also going to be benchmarking what we make against what the current malloc current memory allocator is. So this is the benchmark, as you can see. So this is like yeah, the time taken by our you can say allocator versus time taken by the libc one, and there are other stuff like the memory taken by R1 versus memory taken by the libc one. So these are the benchmarks. We'll also be testing it against it, like how much improvement it is, and to make that improvement, we have to take. We cannot just like we cannot be calling sbrk again and again, because we have to like manage stuff inside what we have like already. So let's first take a look at trace files, because in the last video we forgot about that. Not we, but I forgot about that. So let's do that. Let's take a look at first like short traces, what that is. Sorry. Yeah, v0. Okay. So yeah, A was meant to be allocate, W is meant to be write, and F is meant to be, let me just look into the trace file. Trace. I think I should just make it continuous scroll. Yeah. So this is the trace, real program testing, trace files. It was mentioned somewhere, but I can't find it. I'm pretty sure A meant like allocate, W meant write. Where did I read that? I think it was somewhere else. Maybe inside here. Maybe inside readme. Yeah, it might be inside readme. Yeah. So this is what the traces are looking like. So let me just open it. malloc, and what was it? Short traces. Yeah. And nvim here and v0. So yeah. So this is what we are seeing. So here A means allocate, W means write, yeah, write memory, A means allocate memory, malloc, F means deallocate memory, free, R means reallocate memory, realloc. Okay. So what are these initial things? The traces. They have the file name, trace class, trace directory. I just want to take a look like what are the previous numbers. What does these numbers mean? 20,000, 6, 21. Is it like 20,000 is like the initial memory that we have to allocate? Is it like that? So do. Is it something that like M driver uses? Run your heap checker, put a score. I think it's something that the M driver must be using the initial numbers for. Okay, Okay, let's first PV. Yeah, okay. So A is allocate, and the next number is A allocate pointer ID size, then allocate 2040 bytes at 0, allocate 4010 bytes at 1, allocate 48 at point 2, allocate 4072 at 3, there it is, and free 0, free 1, free 2, free 3, 4, 5. Okay, that's great. This is like the easiest one. F0 is kind of like, okay, allocate write 2040 to 1, write, yeah, write memory, pointer ID and size. Oh, right. Oh, so we have to write like what? Write memory. What does write memory do? Wait, I'm so confused. Pointer ID and size. Pointer ID, size. What does write memory do? Come on. No, it's just write. Okay, which is not the commit. Right. I am not sure what write does. If we even take a look at it, I highly doubt we will find something. So write some debugging. Write up. Okay, let's just skip it. So yeah, we have taken a look at what the trace files look like. Let's take a look at the short traces. Wait, what's the time? Oh, we have a very like short amount of time. This video is going to be really small one, but yeah, let's just do it as quick as possible. So let's look at traces. So ls-la, let's say nvim over here, and yeah, it's the same stuff, it's just bigger. Okay, let's skip these for now. Okay, I should have covered this in the like previous video itself, but yeah, let's go. It's fine, no problem, no problemo. Okay. Exit. Okay, so let's take a look at this one. So wait, how are you guys? Wait, is it visible to you all? Wait, how does it look? I'm taking like this much, and then wait, where is the PDF? Yeah, okay, I think this must be okay. So let's just move. So I think we did cover like how does stack allocation work. So like let's say we get inside a code block, and we just, let's say inside a code block, let me use the board, or should I use the board? Okay. Yeah. Yeah, let's just say, let me full screen this now. Yeah. So let's say this is our, wait, what's this? Okay. So let's say this is our outer block. So let me just move this side. Yeah. So this is our outer block, and this is our inner block. Okay. I should write. My handwriting is great, but on board it's not that good. Okay, yeah. So this is the outer block, this is the inner block. So what happened is like we looked at the previous diagram, which is this, where the heap grows from down to up and the stack grows from top to bottom. So let's say what happened is that stack is like a great thing, it's like a great addition in the code. So what happens is that let's say integer y that we have declared over here and integer z that we have declared over here, these two need to be like destroyed, they need to be annihilated after like when we reach this point of this point inside the code. Why is that? Because it's inside an inner block, it's inside, it is like it is present only for this block, so it needs to be destroyed at this point. So here's how it will look. First our code will start from here, it will reach like, okay, we need integer x, variables are declared on the stack, so x goes over here. This is what I've understood, please don't judge me, I haven't looked it up, it's just what I think. And yeah, this is my assumption. I should have taken a look at it, but okay, I will take a look at it after I guess after this video. So let's say x is declared, x goes onto the stack, then we reach like int y. So this point of the code, int y is declared, so y is added onto the stack, and then we reach int z. Z is z. So yeah, so what happens is that when we do like some kind of calculation, blah 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 blah, and then we reach this point, what happens is that we do not have to like consider the complexity that, oh, we have to like free up memory and we have to like manage the freed up blocks and all, because the thing is that this is one block, so whatever we have allocated inside this block need to be destroyed, like, and like whatever we have declared is like in the like what you can say, this is a inverted stack, but it's on the like top only. So like whatever these contents were, whatever was inside this is declared in the top part of the stack, you can say. So what I have to do, so let's say this was let me just erase this. So let's say this was the stack pointer after, like when we reached like this point of the code, then what we have to simply do is like we have to move this pointer back to x. Why is that? Because now we have destroyed int y and int z, because that's what happens. Variables declared inside a block have a scope only limited to this block. Okay, so after we reach this this point of line, after code, after we reach here, int x also needs to be destroyed, and this is how not x will be destroyed, the pointer will just move, x will stay there and it will be overwritten by the next thing. But okay, this is what happens. So this is like great. Yeah, now we can, let me just keep this aside. Okay, wait, what was like, okay, 1620, this okay, let's go. So that's what happening. Let's say sp is plus equals x, return sp minus x. As we have seen, when we allocate memory, we are returning the initial, like the beginning of the, okay, I'll just show you the next. Yeah, so this is the x, this is a we can say like x bytes of memory. So our sp, which is stack pointer was moved to x positions forward, and we'll be returning sp minus x, which is this point of this point in the memory, which is the starting block of the newly allocated memory, starting address of the newly allocated memory. So yeah, should check for stack overflow. Okay, there was a great pun inside the lecture. it's related to Stack Overflow. Go ahead and watch that lecture. It's really good, 1 hour long, as I've said. Yeah, I'll be completing it afterwards. So that's what is happening. Okay, yeah. So as I've said, like if we have to allocate memory, we have to just move the pointer by x, and whatever we have like we have to write it, and free x bytes just means moving the pointer back by whatever positions, whatever x bytes we want. So should check for stack or the flow. That's great. And allocating and freeing takes O of one time. Must free. So what are the advantages of the stack? Or I should say characteristics. Allocating and freeing takes O of one time. That's great because that's like really great. Must free consistent with stack discipline. Must free consistent with stack discipline. I don't remember what was talked about inside like this part of this time segment, but okay, let's just move ahead. Limited applicability but great when it works. Yeah, limited applicability, and this is the limit. What does that mean? So we cannot allocate like we cannot not the problem is not with allocation, the problem is with freeing. We cannot free up memory whenever we want, right? So if I wanted to like free up integer x, so in this example, let's say I want to completely destroy, let's say in this example, if I want to completely destroy integer x, and my stack already has like integer y and integer z. If let's say my stack has integer x and integer y and integer z, and I just want to free up integer x, I cannot do that because like stack doesn't allow that. I have to only free up like from this, like in this direction. So that was one of the limitations that they discussed about. And 1620 again. What? Okay, this one. That was the limitation. And one can allocate on the call stack using alloca, but this function is deprecated, and compiler is more efficient with fixed size frames. And yeah, one can allocate on the call stack using alloca, but this function is deprecated and the compiler. Yeah, so we looked at like what alloca is, and it's deprecated. I didn't knew that, but yeah, they talk like how compiler is more efficient in allocating stuff. So what's the time remaining? It's 7:37, and the time is 23 minutes in. Okay, so fixed size allocation. So this is our main concern. How are we supposed to manage like the freed up memory? As we have seen, like we can in the heap we can allocate, and we can free up memory like any block of memory that we want. So how are we supposed to manage like the freed up memory? How are we supposed to, let's say I want to allocate, I want like some memory. So what am I supposed to do? Am I supposed to find like some memory inside the like I have to like find what are all the freed up blocks and compare them, like find like the most efficient one, like the best fit, or am I supposed to call SBRK again? So yeah, that's the main concern, and that's what the benchmark depends on. So free list. How does free list work? So let's say this is a free list. This is a like I think it's a doubly linked list, but okay, but yeah. So let's say our freed up block starts from here. Let's the free pointer will point in this block, and a pointer inside this block will point to the next freed up block. Next free block. This free block will point to the next free block, and so on. So they also talked about bitmap execution, where we just instead of like we just like say like we like manage bits and say like okay, if this bit is present over here, that means it must be like a free block. So yeah, bit tricks for allocation. Yeah, this is interesting, but I will tell you what I found more interesting, and which is also more like real world type of thing. But yeah, let's go. So fixed size allocation. So let's say we want to allocate like let's say we have like what you can say I have I have another, you can say, what, I have to like allocate some memory. So this is like the first fit one, but yeah, let's go. So let's say x is equal to free. Let's say I want to allocate one object. So this is for fixed size allocation, by the way. All of these sizes are fixed. So this is like really bad because there will be a lot of internal fragmentation and we don't want that, but let's just discuss it for now. Let's say allocate one object, x is free, x is equal to free, so our x will point to the same place where the free is pointing. So this is what it looks like. X is now free, and then we will set free, the pointer free, to the free next pointer. If we have done data structures and algorithms, this is pretty standard when we are doing like questions related to like linked list or binary search trees or whatever. So yeah, so free will now point to free dash next. So if our free was pointing to this block of memory, then free dash next will be pointing to this memory. So now since we have given the statement where free is equal to free dash next, so our free will now point to this block of memory. So this is what happens. Free is now pointing to the next block and x is still pointing at this block, and we'll just return x where the x is now the new free. Whew. Okay, and now yeah, so whatever this pointer is, it's a garbage pointer. I think they've discussed like how to handle these kind of pointers in the next part, but yeah, I'll take a look at it afterwards. So yeah, now how are we going to free up memory? That is a valid concern. How are we supposed to like free up memory, and how are we supposed to, when the block is freed, how are we supposed to add it into the free list? So let's take a look. I think yeah, let's go. This was for allocation of one object. Let's see what happens for freeing of the object again. So let's say this is the object x that we have to free. Let's say it points, x is pointing to that object, to that data object, data segment block. Let's say x is pointing to that block. X next is equal to free. X will so x next is equal to free. So if you don't remember, x is like pointing to this block, and now we are setting it like x, the next pointer of x will now point to the start pointer of free. So this will now point, sorry, this block, the pointer inside this block will now point to free. So we have successfully added another free object, free block inside the free list, like in the start, not at the end. We have added it into the start. So this is what it looks like. X dash next is equal to free, where the next pointer points to the initial pointer of the free, and then we move the free pointer to x, where the free is now x. Yeah, free is now x. Yeah, that was it. And yeah, the characteristics: allocating and freeing takes O of one time. Good temporal locality. I don't remember that one. Temporal locality, I think it's related to like how far the spread is, like how far the free objects, free blocks of memory are, because if they are like really far away, it can cause like yeah, disk hashing. Yeah, I'll talk about this in a short. So poor spatial locality. Oh no, this must be different. Temporal locality must be different. I don't remember. Let's Google. Why do we say like let's Google? Why is it like not let's search? Temporal locality. Wait, what was that? You don't see anything inside this, right? Okay, yeah, that's great. Temporal locality. Oh, no, not going to read that. What is the difference between spatial locality and temporal locality? Let's take a look. What was temporal locality? I don't remember. Okay. In computer systems, the concept of locality of reference is used to increase the efficiency of the cache memory by trying to predict the further usage of the data. The locality of reference is divided into two parts: the two categories of locality, spatial locality and temporal locality. I guess I understand this what the spatial locality means, but yeah, let's go ahead. Spatial locality is the characteristic of a program whereby it accesses memory locations that are adjacent to each other in the physical profile within a given time frame. Okay. Temporal locality means the probability of the program having access to the same memory address at some period. Okay, both concepts. Let's take a look at temporal locality itself. Temporal locality means that an instruction that is recently executed has a high chance of execution again. Okay. So the instruction is kept in the cache memory such that it can be fetched easily and takes no time to search for the same instruction. Okay. And spatial is just means like the adjacent blocks. Spatial locality means that all the instructions that are stored nearby to the recently executed instruction have a high chance of execution. Yeah, got it. Understood. Uh, Please read this. I will read this for you. Spatial locality means that all those instructions that are stored nearby to the recently executed instruction have a high chance of execution. It refers to the use of data elements, instructions that are relatively close. It is talking in terms of instructions, but yeah, we can apply that to the memory blocks as well. Poor block specialty due to external fragmentation, blocks distributed across virtual memory, which can increase the size of page table and cause disk thrashing. I have looked up those terms, but I cannot discuss them right now. Like I have understood like what disk thrashing means. I've understood like what translation look aside buffer means. I will explain them in tomorrow's video. Right now I can't. I have some stuff to do. But yeah, we have like 10 minutes now. Yeah, let's go. So mitigating external fragmentation, translation look aside buffer. It's like kind of like cache for like the translations of the real the virtual memory and the actual memory, kind of like the page table. So I'll explain in the next video. I'll also keep ready like some stuff. Like right now I'm like exploring. In tomorrow's video I'll try to like keep everything ready so I can just move quickly between every single resource. But yeah, let's go. So keep a free list or free a block of storage if a page becomes empty. I'll discuss this in the next stuff too. Also this one too. So this is the main thing, and okay, this is the main thing, and now we have only 10 minutes. Let's go. It's fine. It's fine. You know. Let's go. Let's go. Variable size allocation. This is the main stuff because we will be allocating, as you look like in the trace files. It's not like we are allocating the same amount, same blocks of memory. We are allocating like different sizes, so we have to be ready at all cost, and for that we need variable size allocation. So for this we use bin free list. What does that mean? So what happens is that we will keep blocks of similar size pointing to like the next block. So let's say what does this 0, 1, 2 R mean? I'll tell you afterwards in the further slides, not afterwards, but yeah. So this is one block of memory pointing to not one block of memory, a block of memory of size 1 pointing to the next size 1, next size 2, next size 1, not size 1. Wait, why am I confusing? I think I'm not only confusing you, I'm confusing myself also. But yeah, let's go. So block of size 1 is pointing to another block of size 1, which is pointing to another block of size 1, which is pointing to another block of size 1. So why is that optimal? So let's say I want to allocate a memory of, let's say, 3 bytes. In the next example, we'll look at what that means. So let's say I want to allocate memory of 3 bytes. So what will we do? We will take log to the base. Here log means we have like 2 at the base. So log 2 3 is equal to 2. Also this is like the ceil function. Yeah. So what does that mean? So let's say we have to allocate a block of size 3. We have to allocate memory of size 3. We cannot allocate it inside a block of size 1, so we will not be looking at this 0, right? Here we have got like 2, so we also cannot allocate into like the block of size 2 because it's 3, we need it contiguously. So we will be storing it at a block which is of size 4. But wait, we don't have a block which is of size 4. We also don't have a block of size 8. We do have a block of size 16, but if we allocate 3 bytes of those 16, then the rest will be like internal fragmentation, and that is like really inefficient. So what do? We break this the memory. We break it into like smaller fragments. Sorry. So here's what we do. We break it into 2 k to the power k to the prime. So k prime is the next memory that we found. If this was like 2, not 2, let's say k dash, which is k prime, is like the next best memory that we have found. So that's what we are going to break it into. So this 16 will be broken into 2 to the power 4, which is k, minus 1, 3. So we'll break it into 8, we'll break it into 4, and we'll break it into another 4. You getting me? So we'll break it into 2 k minus 1, which is 4 minus 1, which is 3, 2 to the power 3. So it will be broken down into 8 blocks. Then it will be broken down into k until it's like k 2 to the power k. So that is it. So this is what it looks like. This is 8 bytes long, this is 4 bytes long, this is 4 bytes long, and this is what it will look like. So we have an additional 4 bytes, and we will move that to like this place. So now when we are doing like other kind of allocation, we can use that block instead of breaking another 16-bit one. So yeah, as you can see, we have one 8 bytes long, one 4 bytes long, another 4 bytes long. So we only need to use one which is 4 bytes long. So we return that 4 bytes long. We then like move the 16-byte stuff into like the 8-byte one into the 3, and the 4-byte one into the 2. I think this video is not like going to be that great because like I am like confusing all of you, but I'm so sorry. Like, okay. This is yeah, this is the coalescing stuff. It's not I think I'll cover it in the next video, but okay. So the main problem, like you will look at this and be like, okay, this is a pretty good structure and this can be really efficient, but I think the main problem over here will be like, how will we be coalescing memory? Because like, okay, we are moving like the block of memory to the next, but how will we like coalesce this? Let's say this block, which was like taken up by the x is equal to 3 process, let's say it is freed up again. So how will we merge them into like the 16-byte one again? Or are we supposed to like keep it at that? Because if we keep it at that, then it will be like broken down again and again and again and again, and all the blocks will be like small. We won't have any big blocks. So at what like how are we supposed to do it? I don't have words. That's what I was blabbing about. So yeah, I guess this will be the main thing. Like, how are we supposed to coalesce memory? How are we supposed to merge memory to make the 16-byte memory again for better efficiency? And yeah, I guess we'll end the video right over here with a question mark. And yeah, that's it. This video is like a terrible one because we didn't have a lot of time. It's 39 minutes long. It's like the shortest video ever out of like 3 videos. But yeah, so that is it. This is a really short one. I don't feel like ending one, but I do have some stuff to do, and I'll be back tomorrow. So there will be like 3 consecutive videos right now. So this was the one. There will be more 2 videos after this. I'll I'll look into how what stuff I can do. Like I was thinking of making like freeing up one of the day in my like schedule to for making another video on Wednesday also. But yeah, I'll be thinking about it. Uh, but yeah, till now it has been great. Like I learned a lot of stuff, but I didn't learn it like on camera. I learned it off camera. Go ahead and watch the video. I'm saying it again. Go ahead and watch the video. It's like great, and let's end it over here. I'm at the Bachane, and I'm an engineer for fun. Bye.